Hi, everyone. Dennis Andrews, Goddard Center Director. I'd like to thank you all for joining me in celebrating International Observe the Moon Night. It's truly a great event, and taking a look up and seeing 250,000 miles away our own moon and understanding what it means to us. I'll tell you what, as a kid, when I was 9 years old when the Apollo 11 landed on the surface of the moon, and Neil Armstrong took that first giant leap for humankind. It was an inspirational event, I'd say. But at the time, though, I didn't fully appreciate what it meant. I didn't realize 250,000 miles away, there are people up on the moon. All I could think about is, how did they get there? More importantly, how did we going to get them back? Sure enough, they did come back safely, though, and it inspired me to think about what the moon does mean, what it can mean, and what it will mean in the future. For many years, though, I wasn't sure what science we could actually derive from the moon or what benefit we could derive from the moon. But I'll tell you what, in recent years, scientists have proven that there's ice there. We look towards the moon to understand it, understand what it means to our Earth, to look to see if we can do in situ resource utilization, perhaps make fuel through the Artemis program, and to expand the presence of humans to the moon and then on to Mars. Truly a great opportunity for us. So the moon means a whole heck of a lot to me, and I know it means a whole heck of a lot to the entire world. It's great. It's a great celestial body. And I'm happy to really be a part of this event today. You know, over the years there have been songs, poems, plays, books, and all sorts of artistic endeavors talking about the moon. So now I'd like to introduce Ann Kinney, the Goddard Deputy Center Director. And Ann is going to celebrate an artistic work that was created by a friend of hers. I think it's very interesting as well. So please join me in welcoming Ann Kinney.
Thanks very much, Dennis. I would like to share with you a poem written by a good friend of mine, Rebecca Elson, who was both an astronomer and a poet, and wrote a poem called "What If There Were No Moon?" This poem is a wonderful combination of the poetics of the moon together with the science of the moon, if you will. And in the background, you can hear a wonderful piece of music called Clair de Lune, Light of the Moon, played by Debussy himself, the composer. So, what if there were no moon? There would be no months, a still sea, no spring tides, no bright nights, occultation of the stars, no face, no moon songs, terror of eclipse, no place to stand and watch the earth rise. So the moon means a great deal to us, and Dennis and I hope you will enjoy this celebration of our dear, near neighbor, the moon.
The Moon. It's our nearest neighbor in space, and data we gather from its features can tell us a lot about the rest of our solar system. And through the eyes of the LRO spacecraft, we can explore the lunar surface in all new ways, in fascinating detail. Our tour begins on the western border, where the near side of the Moon meets the far side. The enormous feature is a lunar crater, and it's known as the Oriental Basin. Here, LRO's terrain map combines with surface gravity measurements from the Grail mission. This data reveals structure in the lunar crust beneath the surface, giving us a window into the geologic features of the Moon's interior. Our next location receives little direct sunlight and has some of the coldest recorded temperatures in the solar system, the South Pole. The highlighted spots signify potential water ice based on temperature readings from LRO's Diviner instrument and reflectance from its laser altimeter LOLA. LOLA also allows us to peer into the darkness of Shackleton Crater by bringing us this digital elevation model. It's 21 kilometers wide and 4 kilometers deep, but it pales in comparison to the largest known impact crater in the Earth-Moon system, the South Pole Aitken Basin. Sitting on the far side, it's 2,500 kilometers across and 13 kilometers deep. We don't yet know exactly how old the basin is, but it was first seen in the 1960s by spacecraft flying around the far side. As much as we use LRO data to investigate areas we can't see from Earth, we also probe familiar territory on the lunar near side to bring back images with an all-new level of detail. This is Tycho Crater. It's around 100 million years old. Here, the Lunar Reconnaissance Orbiter camera captures the central peak with a 100-meter wide boulder at the summit, the origins of which are still a mystery. Continuing across the Moon's near side, we will arrive in an area ripe for future exploration due to the diversity of impact and volcanic materials. It features a prominent crater so bright it's not only visible through telescopes, but also to the naked eye. Welcome to the Aristarchus Plateau. Here, infrared shows the mineral pyroxene in orange and a splash of plagioclase in blue from Aristarchus crater. This region can tell us a lot about the rich volcanic history of the Moon. As much as we study the Moon looking for sites to visit, we also look back at places we've already been. This is because the new data that LRO is gathering helps us reinterpret the geology of familiar places, giving scientists a better understanding of the sequence of events in early lunar history. Here, we descend to the Apollo 17 landing site in the Taurus Littrow Valley, which is deeper than the Grand Canyon. The path the astronauts took over the course of 3 days is shown. The Lunar Reconnaissance Orbiter camera is even able to capture a view of the bottom half of the Apollo 17 lunar lander, which still sits on the surface, as well as the rover vehicle. These images help preserve our accomplishment of human exploration on the Moon's surface. Moving onward, we make our way to our final destination. This location contains regions that exist in permanent shadow, as well as ones that bask in nearly perpetual light. It's the North Pole. Detailed terrain measurements by LOLA allow scientists to model sunlight and shadow at the poles over decades and centuries. Sunlit peaks and crater rims here may be ideal locations for generating solar power for future expeditions to the Moon. This updated visualization of the lunar landscape stands as a testament to the functionality and abilities of the Lunar Reconnaissance Orbiter spacecraft. And as the mission continues to gather data, it will provide us with many more opportunities to take a tour of our Moon.
sea of clothes that we could only see from afar. Come on, let's go. Your dreams are passing by. We can fly far away from here, defying gravity. We'll soar beyond the atmosphere, and we will see things we've never seen before. We'll open up a door to what new
Hey, I'm Jacob Richardson at NASA Goddard Space Flight Center, and I'm a planetary geologist, and I study volcanoes. NASA studies volcanoes because not only are volcanoes actively erupting every day on the Earth, but there are also hundreds and thousands of volcanoes on all sorts of planets around the solar system and maybe even beyond to other solar systems. So today I'll show you a demonstration where you can safely erupt your own small volcano inside your home. And to start, let's look at what a volcano is. So since I study volcanoes, I've drawn one for you here on this piece of paper. And you can see that volcanoes are often mountains, and they often have holes in the center. So let's look at the inside of this volcano. Here I've drawn the volcanic vent. This is the pathway filled with magma, where magma goes from the inside of a planet to the outside, and you can see it's erupting right now. So this is our model that we have here. And magma is made up of three different things. We have molten rock, we have solid rock, and we have gas. And all of these inside of a volcanic vent that we have as our cup are all mixed together, waiting to erupt. So here we have a film canister that will represent the volcanic gas that's inside of the magma in our demonstration. Now, when magma comes up closer to the surface of any planet, the gas expands, and when it gets very close to the surface, it expands very quickly, and that causes explosive eruptions. So in this demonstration, we need to fill this with a gas that will expand until the film canister will break apart. What you'll need for this demonstration are safety goggles, some film canisters, we got ours on the internet, and some Alka-Seltzer tablets or effervescence tablets, some spare change, also some table tennis balls, a clear plastic cup, and some water. Alright, so first we'll put on our safety goggles, and now that we have these on, we can begin doing some science. So I'll take one of these film canisters, and to weigh it down, I'll load it up with our spare change. This will just add weight so it doesn't go flying during this experiment. Now I'm going to take our volcanic vent and put it in the center of the table and move everything else a little far away from it. And I have my solids ready to go to put into the volcano right before it erupts. So to make the gas, we're going to use effervescing tablets, and we're also going to use some water. So I'm going to fill this film canister up with just a little bit of water. Maybe halfway would be fine. The next part's a little quick. We're just going to add this tablet into this film canister and close it up good and tight and put it inside of our volcanic vent facing up. And then we're going to put the ping pong balls right on top of that and stand back and watch. Let's do it. So there you have it, your own volcanic eruption. So now let's do this just a little bit bigger. How about a trash can volcano? So in this trash can volcano, everything will be a little bit bigger. Instead of a plastic cup, we'll use a plastic trash can. Instead of ping pong balls for the solid rock, we'll use wiffle balls. And now we'll add some water for the molten rock. For the gas, instead of a film canister, we're going to upgrade to an empty soda pop bottle. And instead of effervescence tablets and water, we're actually going to be using liquid nitrogen in this to make the eruption. Liquid nitrogen is really cold, and we're going to use these gloves, which are insulated, to protect our hands from any exposure to that. All right, we're ready to get started, and to get some help, I've enlisted my NASA colleague, Kayla Berry, to help me pour this liquid nitrogen into our soda pop bottle. Are you ready?
Ready.
So the science demonstrations that you saw today are exactly the same thing that happens in volcanoes on Earth and in the ancient pasts of the Moon and Mars and maybe present-day Venus. Now, what happens in a volcano to make it explosive is that the gas very quickly expands, and that creates some sort of a bubble that sometimes bursts and makes these explosive eruptions. So in other planets where they have thicker or thinner atmospheres, that can make explosions smaller or bigger. And that's what we study here at NASA Goddard.
Welcome! I'd like to talk to you today about geology and art. My name is Sarah Noble, and I'm a lunar geologist and also an artist. Here I am in the desert playing with some moon rovers, and this is one of my paintings. At its most basic level, art can be broken down into just 5 elements: shape, line, color, value, and texture. For the most part, these are the same clues that geologists use when we look at images of other planets to understand what is happening and what processes have shaped the planet's surface. Let's take a closer look at each of these elements. The first one is shape. The most common shape we find across the solar system are circles. These often indicate impact craters. There's a lot of stuff floating around our solar system, and sometimes bits run into other bits and leave behind these scars. This crater, Lunar crater on the Moon, is one of my favorites because it's just so perfectly round. But not all craters are. Here's an image from the surface of Callisto, one of Jupiter's moons. And you can see that most of the craters here are round-ish, but they aren't perfectly round. Things like the angle of impact, the existing topography, the underlying structure, and post-impact slumping and modifications can all influence the exact shape. You will find things, though, that are definitely not round. Blobby shapes usually indicate volcanoes, like in this image of Aina D. It's one of a mysterious class of lunar volcanic features called IMPs, irregular mare patches. IMPs are a hot topic among lunar geologists today. Some think that these features are ancient, billions of years old, while others think that they're really young, only tens of millions of years old. That's really young to a geologist. Figuring out which is true will have big implications for how we think the Moon cooled, because up until recently we thought that all volcanism on the Moon stopped about 1 billion years ago. Sometimes blob shapes can indicate lakes, but we don't have any of those on our Moon. There is one moon in our solar system that does, though. It's Titan. Titan is one of Saturn's moons. If you look at it with your naked eye, it just looks like a big orange ball because it has this thick, hazy atmosphere. But if you look at it in certain wavelengths, you can see through the haze, and below it are these amazing lakes. They're not filled with water like lakes on Earth. It's way too cold out there for liquid water. Instead, they're filled with liquid methane. But we think that Titan has a methane cycle that works just like our water cycle, with clouds and rain and streams and lakes. Pretty cool. Okay, moving on to line. Line comes in 2 basic varieties, straight and curvy. Straight lines are often a sign of tectonic activity, like these awesome faults and fractures on Pluto's moon Charon, whereas curvy lines usually suggest something is flowing, like a meandering stream or a lava flow. We do have lines on the Moon from tectonic activities. They are smaller and not quite as impressive as the ones on Charon. These little faults are called wrinkle ridges, and we find them all over the Moon. Some of them, like the ones shown here, are really young. How do we know they're young? Well, you can see how they cut through most of the craters in this image. That means that the crater had to already be there when the ridge formed, which means the ridge is younger. We think that these ridges may be forming even today. The Moon is still cooling, and as it cools, it shrinks. These ridges are the result of that contraction. Okay, color. Color also comes in 2 varieties, true color and added. True color means what your eye would see if you looked through a big telescope or visited in person. Here are some true color images of Jupiter's biggest moons. Isn't it amazing that they're all so different from each other? The Moon's true color is pretty boring. It really is pretty much just shades of gray. But as geologists, we often use color to help us visualize things. Like the image on the left here uses color to represent different kinds of mineralogy to help us understand what the variation in composition is across the moon's surface. On the right, the colors represent topography. Reds and yellows are high points. Blues and purples are low. So here's one place where artists and geologists use different words. Artists use the term value, while geologists have their own word, albedo. But they mean pretty much the same thing, how light or dark something is. The moon has some great examples of this. Here's a couple of beautiful impact craters on the moon. Look at the amazing patterns of light and dark. This happens because the moon is exposed to the space environment, which causes the surface to get darker over time. But when you get an impact, it pulls up fresh material from below that's still bright. These are fresh craters, but over time, these bright patterns will fade away. The moon also has these other cool patterns called swirls that are like my favorite thing. Aren't they beautiful? They're also mysterious. We don't know what causes these to form. We know that it's related to magnetic fields in the rocks below them, but we don't know what caused the magnetic fields or why the patterns appear. Okay, our last element is texture, which is a bit hard to show in 2 dimensions. Texture is the quality of the surface. Is it rough? Is it smooth? What do you think of the textures in these images from the Lunar Reconnaissance Orbiter camera? Can you imagine what it would feel like to walk across these surfaces in bare feet? So that's it. We covered all 5 elements. I hope you learned a little bit about lunar geology tonight, and I hope I inspired you to create some of your own lunar art. I wanted to end by sharing a couple of my paintings so you can see how I use shape, line, color, value, and texture to interpret the moon. The top one of these is one of those lunar swirls we just talked about, and you can see how I used value, highlights, and shading to give the crater some dimensions and texture and to make it seem 3-dimensional. The bottom painting is a more abstracted landscape, and you can see how I used line and color to focus the viewer's attention on the oasis that is the Earth, hovering over the alien landscape of the moon's surface. Now it's your turn. Go forth and make some art. And if you're so inclined, please share it with us. I would love to see what your imaginations unleash.
Watching Apollo footage of astronauts doing geology on the surface of the moon is a really great way to think about preparing for Artemis, for putting people on the lunar surface once again. We learn a lot in how they did science operations on the moon and what it's like to work on the moon. You see them doing geology. You see them taking rock samples, putting in a drive tube to take a core sample. You see them bouncing along the surface of the moon on the lunar rover that they used in Apollo 15 through 17. So it's a great way to help drive technology development for the next generation of spacesuits and geology sampling tools.
There's these facilities that help us train like we are on the lunar surface. You know, these 1.6G offload systems or putting people in the aquatic environment are great ways to train the mobility part, right? Like, what can you do and how different does it feel to be in 1.6G and do these tasks?
We've been training astronauts in geology and geoscience for decades now. The Apollo astronauts had literally hundreds of hours of training in geology before they flew to the moon. It's often said that the Apollo astronauts had the equivalent of a master's degree in geology by the time they flew to the moon. In the intervening decades since Apollo, we've been training astronauts who fly to the International Space Station because when they're on the ISS, they spend time observing the Earth. looking out the window, taking pictures of what they see on the Earth's surface. Now that we're looking at putting astronauts on the surface of the moon, we also take them into the field. We take them to field sites here on Earth that resemble field sites that we expect them to see on the moon.
That's the reason why we take them out into places that are unique, like volcanic landscapes or places that are analogous to the lunar surface, to train them on the scale and fidelity of science that you just can't recreate in these facilities.
And so by combining this classroom and field training, we're able to prep them for fundamentals of geology, the major driving lunar science questions that we have that we hope to address with the Artemis program, and teaching them how to do field work in relevant analog environments.
For just science aspects of developing new spacesuits, can it get you to where you need to go? And then once you get there, can you do the cool science that you need to do? And so that's, can you move effectively and efficiently in the suit to be able to collect the samples or use the tools or the instruments? For the visibility, it's like, can you make the necessary observations that you need to? Or does the suit have the lights on it that it needs to illuminate the surface and make the observations you need to? The lunar South Pole holds tremendous resources that are going to allow us to continue to explore. This is a place that we've never been before. There's so much to be learned from getting boots on the ground and exploring a unique place that challenges us as humans and also helps us develop technologies that make our everyday life that much better.
We think there might be volatiles present at the South Pole. By using these volatiles, we'll be able to do things like create drinking water, create rocket fuel to launch astronauts back to Earth. And so by harnessing the power of the land, we'll be able to help astronauts establish that long-term sustainable presence.
It's human nature to explore. Pushing our boundaries and exploring our universe is, I think, just one of those things that's just stuck in our human nature, and that we need to do it in order to understand the world around us, including our Earth and our solar system.
Hi everyone, welcome again to International Observe the Moon Night. I am Dr. Casey Honeyball, and I would like to tell you about my search for water on the moon. So with the Artemis program, NASA will land the first woman and next man on the moon by year 2024 with the goal of building a sustainable human presence. But in order to do this, we must understand what and how much we need to bring with us. And the most important thing for human life is water. An astronaut cannot survive on the moon more than a few days without drinkable water. This water could also be broken down to provide breathable oxygen and to produce rocket fuel, allowing humanity to travel even farther into our solar system. But water is expensive to launch to space, and so finding water on the moon that we can use is important for building a sustainable human presence. Currently, we do know that water exists on the moon from observations with spacecraft, telescopes, and Apollo samples. But what we need to understand is how much water is there and how can we extract it. So you may be wondering, well, how did water get to the moon in the first place? Well, there's a few ways. One way is when the moon was first formed, and before it formed a solid surface, comets carrying water impacted the moon and left behind water in the lunar interior. This internal water would later be erupted onto the surface of the moon through volcanic events. Another way is that water is created on the moon through interactions of the solar wind with the lunar surface. Solar wind is mainly made up of hydrogen, and when this hydrogen hits the moon, it can react with oxygen in lunar minerals and form water. And one other major way that water can get to the moon is through recent meteorite impacts. Meteorites, like the comets, can carry water to the moon or produce water during an impact. But where can we find this water? Well, it could be trapped inside permanently shadowed regions at the lunar poles that are super cold because they never receive any sunlight. At places like this, the water can be trapped as frost, like you might see on your grass on the cold winter morning. Water can also stick to surfaces of lunar grains as it hops around the hot lunar surface looking for a colder place to live, or during a hop, it could be lost to space. Water from inside the moon can be trapped in volcanic glasses from when they erupted billions of years ago. And lastly, impacts can store water in glass, like an insect trapped in amber. When a meteorite hits the moon, it melts some of the lunar surface, and experiments have shown that water from the meteorite can be trapped in the glass that forms from the impact. So where this water lives is important for understanding how to extract the water and use it as a resource. So how do I study and look for hydration on the moon? One way is by looking at the moon with the NASA Infrared Telescope facility located in Hawaii, shown in this top picture during a lunar eclipse. Specifically, I look at the 3-micron infrared wavelength that tells me if water and its close cousin hydroxyl are present. What we find when we look at this 3-micron band is that it changes in strength with lunar time of day, latitude, and composition. This indicates that the amount of hydration on the moon is changing. This image of the moon in the bottom corner shows in blue where we are seeing hydration and showing how the hydration is changing with latitude. But there's an issue with the 3-micron band, and that it cannot distinguish between water and hydroxyl. So in order to separate water from hydroxyl, we created a new method for detecting purely water on the moon. Instead of looking at the 3-micron band, we shift to 6 microns. Now this isn't a big shift, but at 6 microns, water has a unique spectral fingerprint. This technique is new to the moon, but 6-micron water has been detected on Apollo samples, meteorites, asteroids, and on Mars. 6-micron observations of the moon are hard though because Earth's atmosphere does not allow light at 6 microns to reach ground-based telescopes. And currently, because this is new to lunar science, there are no existing or planned lunar spacecraft capable of 6-micron observations of the moon. So instead, we are using the NASA Stratospheric Observatory for Infrared Astronomy, or SOFIA, to make the first observations of the moon at 6 microns looking for water. SOFIA is an airborne telescope flown on a Boeing 747 that flies at 45,000 feet. This picture on the left is me with the SOFIA plane on my first observing run. The middle is the SOFIA plane at sunset, and the right is a picture of me observing the moon inside the SOFIA plane. So how do the IRTF and SOFIA telescopes support the Artemis program? With these two telescopes, we can map water and hydroxyl on the moon. These maps will allow us to estimate how much water versus hydroxyl is present at different locations. One type of location that is of particular interest is volcanic deposits because they may concentrate water that can be used as a resource. So my future work will be to use the IRTF and SOFIA telescopes to look at these volcanic deposits like the Aristarchus region shown here. Currently, we know that these volcanic deposits have high hydration through the 3-micron observations. But like I said before, at 3 microns, we cannot distinguish between water and hydroxyl. So with the IRTF and SOFIA, we can separate water from hydroxyl. The maps that we create of the volcanic deposits will provide insights into the amount of water present and how to extract it. If we find that these volcanic deposits on the moon have high abundances of water, these may become landing sites for the Artemis crews. And the water that they find can be used by the astronauts. Thank you again for attending International Observe the Moon Night.
50 years ago, we went to the moon. We called it Apollo.
What many people don't know is that Apollo had a twin.
She was a woman named Artemis,
goddess of the moon.
We are returning to the moon
as a new generation of explorers.
This time to stay.
And to prepare to achieve humanity's next giant leap of sending the first human missions to Mars.
We believe our course will redefine what is possible.
That we will discover life-saving,
earth-changing science.
And that the challenges ahead will inspire generations.
This is our manifest.
For all who wondered if we could return.
For all who dreamed of pressing beyond.
This is your calling.
We go for all of America.
We go. We go as the Artemis generation.
We go.
All I know is you give me that feeling like I never wanna tell you lies. And I just wanna take a chance.